Hello everybody. I'm Pasha Shamis from NVIDIA, and it's true honor to introduce today's speaker, someone I had the privilege knowing and working alongside for over 20 years. Pavan is a principal research scientist at Meta AI, where he leads transformative work in GPU training system and AI communications libraries. His contributions have been pivotal in building some of the Meta's most advanced AI supercomputer systems, including Grand Teton architecture, which supports Meta's most demanding AI workloads, ranging from recommendations models to the generative AI models like Llama. Pavan's influence extends far beyond his current role. During his time at Argonne National Laboratory, he made significant strides in the design and implementation of communication runtime systems and training models. I had distinct pleasure of collaboration with him on projects like MPI and UCX, where his expertise and commitment were truly inspiring. His work on MPICH project, UCX, Argobots has been impacting supercomputers and commercial products around the globe. Today, Pavan will be sharing insights into one of the Meta's latest and most exciting projects, Llama 3. This is not just another AI model, it's groundbreaking achievement that showcases state-of-the-art capabilities in everything from general knowledge, generative AI knowledge, and multilingual translation. Pavan will give us an exclusive look at the massive infrastructure behind Llama 3 and diving into the challenges and innovations that make it possible. Please join me welcoming my colleague and friend, Dr. Pavan Balaji.
Thank you, Pasha. Thank you for the very kind introduction. And thank you for the invite to come here and speak. It's a great pleasure and honor to be here. I think I just started attending Hot Interconnects 20 years ago as a grad student. It's a pleasure to be back here to give this talk. I'm going to share my slides. I have a cheesy video. I don't know if it will play or not, or the volume will go through or not, but we'll try. Okay, can you guys see my slides?
Yeah, you probably want to switch to presenter mode.
Yeah. Okay, I'll get started in a second. We'll try with the video. If it doesn't work, we'll move on, but let's give it a shot. Okay, so my talk is on Llama 3. I think it's the most recent model that we have released, 3.1 actually. The talk I will try to cover a little bit of the infrastructure details. The talk is not about the model itself, but about the infrastructure that's powering the model, both from a training and from a serving perspective. Okay, so here's the cheesy video. I'm going to play it. Let me know if the volume is coming through. If it's not, we'll skip it.
Infrastructure fundamentally is what I call the engine behind the growth of this company. We have been building data centers since 2010. We're talking about serving maybe a half of humanity. Now, when we're talking about AI, you need a similar engine behind AI so that AI can achieve the potential that we are sort of dreaming.
AI workloads are growing at a pace of 1,000x every 2 years. I mean, just contemplating what that means for our systems, our silicon, our software stack, we're in the middle of a pivot to the next age of information. The models themselves are becoming hundreds or thousands of times larger and more complex. And what this is going to require is infrastructure at the exaflop level.
We're reimagining everything we do about our infrastructure for AI. We're creating data centers that are specific for AI. We're creating new hardware, including our own silicon. We're building out new kinds of network architectures. We're reimagining the software stack like PyTorch. Thousands of engineers are innovating on this large-scale infrastructure that's built specifically for AI.
Okay, that was my cheesy video. Let me move on. Hopefully the volume came through. I'm having trouble with that. Oops.
Yes,
Okay.
it was audible.
All right, great. Okay, so just a bit of a video to talk about what the kind of infrastructure we're building at Meta. So let me take a step back over here and let me talk about generative AI models at Meta. For Meta, generative AI has been relatively new, just a few years old, 2.5 years old. And most of the investment over here has been in the context of Llama. So the idea is to build out models that can create new realistic content, like open up new possibilities for more creative applications to be built out. We started out with Llama a few years ago, Llama 2, and most recently, earlier this year, we released Llama 3 in 2 batches. First batch, we released 8 billion and 70 billion parameter models. And very recently, we released our large 405 billion parameter model. This is the largest dense parameter model that that's used in production today. So it's a big deal, and it is it's the only open model that is competitive with the top closed models in a variety of benchmarks across the board. That's just the model. Right? The model works in the background. It's like a mathematical equation. It runs in the background. There are products that you can interact with this model. Meta AI was what was recently announced. You have a picture of Zuck over there presenting the announcement. It's integrated into Meta's family of apps, WhatsApp, Instagram, whatever. So Meta AI is how you interact with the model. You go and type your query. At the back end, it goes and uses Llama 3 or Llama 3.1 to be more precise to come back with the answers that you're looking for. A few statistics on the right-hand side if you're interested in looking at that. So we come a long way in the last few years over here. Here is a picture of where the evolution worked, how the evolution went. The left-hand side picture, this is the same prompt at the top. This was around the time of Llama 1. With the same prompt, same query, you can see on the left-hand side, we get a decent picture, but it's cartoonish in some sense, right? It's good, but it's not that realistic. Fast forward to around mid 2023, about 6 to 9 months later, and about the Llama 2 generation, the outcome of the prompt is much more realistic, right? It's more realistic, more richer colors, and all of that stuff. This is still in the previous generation Llama 2. Coming to 2024, this is with Llama 3. Of course, we have all of the realistic content that we had with Llama 2, but this enhances a bit more with respect to two axes, if you will. The first is more accuracy. The model has to be more accurate, and we achieve that by using much larger models and more data to train that. So 405 billion parameters, a lot of data. I'll talk about that in a bit. And the second axis is with respect to speed, how fast we can answer queries on that. Unfortunately, this accuracy and speed they're strong duals. It's very hard to achieve both. You can gain a lot of accuracy by making the model very large, training with a lot of data. But in doing that, you usually lose speed of serving because the model is too large to serve. Achieving both together, that's the trick, and that's where the infrastructure comes in. We build large supercomputers, we build very fast supercomputers so that we can achieve very fast responses, very fast queries, while still maintaining the high accuracy that comes from the large models. We'll talk about the infrastructure. I'll focus a little bit more on the network aspect of it, network and communication libraries aspects of it. But the whole infrastructure itself is important to be able to achieve both of these at the same time. A little bit about a quick training versus serving 101, just to kind of warm up the crowd on this. There are two parts to be able to run the model, to be able to serve the model, for users to be able to use it. The first part is we train the model. So we take a lot of data. We take basically an untrained neural network. You can think of it as a neural network with the weights initialized to random values for simplicity. Then you train it with a large amount of data and end up with a trained model. But this takes a long process. It takes a lot of GPUs, a huge network. It takes months to train. And at the end of it, we end up with a trained model. So the weights are optimized for this data set. Once the training is completed, this model goes through a bunch of like pruning and other optimizations, and then it's ready for serving for the users. This is when a new query comes in. We serve the model based on this trained, we serve the query based on this trained model that we have in the backend. So you can see that the larger the trained model is, the more harder the serving gets. So it's a trade-off between these two that we need to handle. Okay, let me jump into the training at a scale, a little bit of it. I'll talk about four parts of it. I'll focus more on performance and reliability, but I'll cover four subtopics within that. Compute side, the storage aspects, network, of course, and the software stack associated with it. So first of all, the compute part. Meta uses first of all, Meta has a large infrastructure with dozens of data centers around the world. And AI is a big part of it. And a lot of our AI, not all, but a lot of our AI infrastructure is powered by multiple types of GPUs, as well as our internal silicon. For example, we buy a lot of GPUs from NVIDIA. We have our portfolio has about 350,000 GPUs by the end of this year. And if you include all other kinds of GPUs that we have, like for example, A100s or other vendors and so on, we have equivalent of 600,000 H100 GPUs in the system. So that's a very large set of GPUs that are available. And of course, we need to kind of combine them to make a supercomputer out of it. So we recently, 2 years ago, announced a architecture called Grand Teton. It's openly available on OCP. You can take a look at it. Here's a rough TLDR of how the architecture looks like. It's a tightly coupled chassis architecture, which has CPUs, 8 H100 GPUs inside a box, NVLink switches within the box, PCI switches. We have a backend RDMA NIC for each of the GPUs. So each GPU gets a 400 gig RDMA NIC, and some additional front-end NICs where TCP/IP traffic goes, like for loading data and checkpointing and things of that sort. And we have two. So this is one chassis, 8 GPUs in one chassis. We have 2 chassis per rack. So a rack has 16 GPUs. And we have multiple racks connected together in 2 layers. One layer, I'll talk a little bit more about that, but one layer has full bisection bandwidth, and then we have multiple of those units, what we call AI zones, connected together in a tapered manner. Okay, that's just the architecture of the system. Let's talk a little bit about Llama 3. So Llama 3 training was supported by using 2 large supercomputers, each with about 24,000 H100 GPUs. So this is an aggregate of about 200 exaflops of FP8 performance at 2-to-1 sparsity. This is a bit misleading statement. It's actually 100 exaflops because we don't use the sparsity, but it's a term. I was just being consistent with the term, the number that is floating around elsewhere. So about 24,000 H100 GPUs, let's say about 100 exaflops of peak FP8 performance. So this is peak. The achieved performance is, of course, lower than that. And these are 2 supercomputers. One was built with Rocky. The other was built with InfiniBand. Other than the network difference, everything else is identical between these 2 supercomputers. And both are based on Meta's Grand Teton architecture. So these supercomputers were mainly the ones used for our training. We used a few other supercomputers for other smaller pieces, but bulk of the work was on these supercomputers. That's the compute side itself. Let's talk a little bit about the data and storage. Of course, having just a lot of compute is not particularly helpful if our data we don't have a lot of data to train with. Not just a lot of data, but high quality data. So we spend a lot of time taking data and bucketizing that, cleaning that up, and so on, so that we can get good, high quality data that we can train our models with. The Llama 3 paper has a lot more details of all of the work that goes on in it with respect to what kind of cleaning happens on the data sets. So you can take a look at that for more details. This was trained on 15 trillion tokens of data. That's a fairly large data set. It's not the largest data set out there. I think other models have trained on even larger, like 40 trillion, I believe. But this one was trained on 15 trillion tokens. It's 7 times larger than Llama 2, and it's a mix of publicly available online data. Now, this is 15 trillion tokens of data. Then there is a question of the number of epochs trained. So the way it's trained is that not all of the data is replicated. Some parts of the data are replicated. So you get this like a mini epoch sort of behavior if you replicate some parts of the data. So some parts that are more important to be trained can get replicated more. Some parts that are not as important don't get replicated as much. And this was the entire storage infrastructure was based on Flash media. We used a Meta's Tectonic distributed storage solution. I'll talk a little bit more about that in a second as well. We also co-developed an NFS solution with Hammerspace and so on for interactive debugging. Okay, let's look at a very high-level, top-level view of the storage system. So this is a very simple cartoon. I think most people who work on training systems know that there's a lot more that happens, not just this part, but just bear with me as I walk through the simple model. So we start the model. Every iteration, we ingest data from the storage system to see, okay, here is the data that I need to train for this iteration or for the next few iterations. And at some point, after some number of iterations, we checkpoint our state. And every iteration we're ingesting data, every few iterations we are checkpointing data, and we continue through this loop many, many times, and eventually come to an end of the model once we have run out of data or we have reached our desired accuracy. The ingest part is, of course, entirely read-based, and it's synchronizing. So we need all of the data before we can start training. And the checkpoint is, of course, entirely write-based. Pasha, did you have a hand up? Pasha, your hand is up.
What is the question, Pavan?
I think Pasha's hand is up. I don't know if you have a question or. Okay.
It was a mistake, ignore it. Sorry about this. I clicked
no
on
problem.
something.
Okay. Okay, so GenAI training storage needs. So one thing we, as I mentioned earlier, the GenAI was relatively new for Meta. Earlier, of course, we used to use AI, but we used to use AI in a different context. We used to use it for example, our recommendation models, as well as use our storage systems for things like, our regular traditional data warehouse. For example, you upload your pictures to Facebook that goes and sits in a data warehouse somewhere. The storage needs changed dramatically compared with what the traditional usage of the storage was. Like, for example, when you're using in traditional warehouse terms, you have long, consistent stream I/O. The throughput matters more, not the latency. And storage is typically the expensive part over there. For GenAI training, it's a bit of a reversal. The I/O is very short and bursty because we are loading ingest data. We are checkpointing every once in a while, but it's not like a continuous stream of I/O. So that changes a lot. Latency matters a lot. The training is synchronous across thousands of GPUs. So the P90, P99 latency, right? When the last person gets their data, that matters a lot. So we have to be very careful about that part because of the synchronous training aspect. And of course, storage is the cheaper aspect, so we can afford to do things that where, for example, replicate things or create new storage devices as needed. We've played around with a lot of various solutions, vendor provided solutions, but eventually we decided to build our own for two reasons. The first reason is doesn't work. Other solutions, vendor solutions that we evaluated, one, don't work at scale in some cases, or two, the big one, they did not offer the strict privacy and security that Meta requires. This is a big no-no. If the solution doesn't offer the Meta standards of privacy and security, it doesn't matter how good the solution is. It's just not going to use it because we can get sued if we are not maintaining the privacy correctly. So at the end of the day, we went with the system called Tectonic FS. This is Meta's exabyte scale distributed file system. It has several advantages with respect to scalability. It's a simplified semantics. It's append-only file semantics and so on. But it's sufficient for what we need for our GenAI workloads. It doesn't have some cool features that other file systems have, like, for example, no NFS look and feel. But that's it's okay. We can modify our applications. We can deal with those sort of problems. Here's a quick picture of how this was working. So when we are running our traditional applications, right, the traditional Facebook streaming or whatever it is, or Facebook wall, our storage access P99 latencies were, it's that you can see the picture on the left over there. They're okay, less than a certain threshold. But the moment we add things like AI checkpointing, you can see on the right-hand side, there's a huge bursty traffic. Because every time you're doing a checkpoint, we're dumping a ton of data to the storage. And we have this, 24,000 or two supercomputers combined, 48,000 GPUs all dumping data at the same time. The entire job is dumping data at the same time, which creates this giant burst of IO, and the P99 latencies they shoot up every once in a while. Again, I want to remind folks that the P99 latency matters a lot because this is synchronous training. Even if one process is delayed, all processes have to wait. It doesn't matter that my average latency was great. What matters is what my P99 latency is, because all processes have to wait. Now, we do some buffering, like, for example, we do things like, try to not wait for the checkpoint to finish so that we can move forward and so on. But there is only so much buffering you can do. Eventually, the latency difference will catch up with us. Okay, that's with respect to storage. Let's switch gears here and talk a little bit about the network aspect. So I mentioned this a little bit earlier. We have a multi-layer switch architecture. We have a rack contains 2 nodes, each nodes with 8 GPUs. So at the bottom, you'll see there are 16 GPU racks, and each rack has a switch called a rack switch, or top of rack switch. It's not actually at the top of the rack, but it's called a top of rack switch. Then the second layer, we connect a bunch of these racks together with the first level or second level switches, if you will, which are called training cluster switches, CTSWs, which together, this is full bisection bandwidth. So we get in this training cluster, that subset at the bottom left, you get full bisection bandwidth. Now, I think everyone in this group would know, building a fat tree with full bisection bandwidth does not mean that you will not have network collisions. It's not a crossbar. So you will still have network collisions, and that's something we need to deal with. But at least from a theoretical perspective, there is full bisection bandwidth in that set. Then you have multiple of these sets that are combined together. I should point out at the bottom, there are 256 such racks at the bottom within one training switch. And we have multiple of these clusters, what we call AI zones, connected together with a third level switch, aggregation switches, to form the overall supercomputer. The aggregation switch is tapered at a 7:1 granularity, 7:1 subscription. So communication between these AI zones is going to be slower. So we need to be careful how we are communicating between them and how much we are communicating between them. Okay, performance at scale. So first thing I would point out is I would point out a paper over here. Multi-stage networks are not crossbars. This is from Torsten, like from 20 years ago. It's a very old paper. I think it might have been from Hot Interconnects. I don't fully remember. It's a recommended reading. I would highly recommend looking through that. Basically, what it says is that irrespective of what we do, unless we are very, very, very careful, in most practical cases, if you have a full fat tree network, it's almost impossible to avoid collisions, network collisions. So we have to deal with that. There are some ways we can avoid it, but when unless we do a global collective, it's very hard to do that. And other aspect is that why do we have such a large network? Why can't we fit more inside each rack switch, for example? This is more to do with power constraints. I'll talk a little bit more about this in later as well. But many times power constraints require us to spread out our GPUs much more further away. So because they are more spread out, we need more levels of switches. We can't as densely pack them as some others might be able to. So that creates other challenges for us. For example, we have a larger network that we need to deal with. We have more collisions, more latencies, etc., that we have to deal with to get around that. And last thing, one of the things we noticed that there are a lot of excellent papers out there that talk about how we can do all sorts of optimizations in various cases. But many of them assume that the networks are well behaved, like nothing goes down. Every once in a while, a node will go down, and we need to be able to restart the job with the remaining nodes. So we'll not have very well behaved networks all the time or well behaved systems all the time. What sometimes we refer to as corner cases are often front and center for these production systems. I'll give you a simple example over here. On the right-hand side, let's pick any collective algorithm, doesn't matter which one. Let's say Algather. There are three types of algorithms. We have seen many papers on this, as you might imagine. There is a full mesh algorithm where each process is directly sending data to all other processes. You can do a logarithmic algorithm like a tree or recursive doubling or whatever other algorithm you can think of. Or you can do a linear algorithm like a ring. We might think that in all cases, the full mesh should do better because I'm sending the same amount of data, but I'm doing a constant number of hops, whereas logarithmic might do better. Whereas ring, the same amount of data, I'm using a lot more steps to do the exchange, so it would be worse. It's not always the case. In some cases, the number of hash collisions that can occur, the network route collisions that can occur while I'm dumping data in a full mesh might actually make it worse than, for example, doing a logarithmic algorithm or even a ring algorithm in some cases. So something to keep in mind where a fat tree is not the same thing as a crossbar. We will have route collisions, we will have hash collisions, and we need to deal with that. And our algorithms need to be able to should be aware of that for best performance. One example I want to call out with respect to static routing. So here's the same picture from the last slide, but shown slightly differently. I have 3 racks over here. Each rack has 2 servers, server 1, 2, 3, 4, 5, 6. Now, let's assume that originally my job requires 4 servers, 32 GPUs. And originally I was using server 1, 2, 3, 4. Okay. And the way my routing was set up was that if I'm sending to the odd numbered server, I will go through the first half of CTSWs, and the first half of the RTSW ports. If I'm going to the even numbered server, I'll go to the second half ports of RTSWs and second half CTSW switches. Now, let's say that server 4 dies for some reason. There's a fault, whatever, it has to be taken offline. And I get allocated a new server, server 5. So it's still a 4-node job, but now I have server 1, 2, 3, and 5. In this case, because both server 3 and 5 are odd-numbered servers, all of my traffic, both to server 3 and server 5, are going through just half the switches and half the cores, half the ports in RTSW and half the core switches. This obviously creates a route collision. We can think of other static configurations as well, but in reality, almost no static routing config can solve this problem because there will always be some failure case where I will have route conflicts because of static routing. So the obvious question is, why not adaptive routing? Well, that's more to do with physical distances and latency. Let me check the time, 10:30. Okay. So here's a picture of our Meta's Arizona data center. You can see that this is the huge spread. Physical distance-wise, it's huge. There's a huge spread. And power constraints often force us to spread these GPUs out over very large distances, right? Because they might be coming from different substations. The power or the cooling might not be able to handle a very densely packed GPU layout and so on. Now, it's very hard for us to do adaptive routing over here because the NIC needs to maintain a large window of out-of-order packets just because my bandwidth delay product is much larger. Physical distance, the speed of light, my delay, my latency is much larger. So bandwidth delay product might make it just hard to be able to do full out-of-order on very high latency networks. We need more custom transports to be able to handle this, maybe more flexible software than verbs. Maybe libfabric. I'm supposed to say also UCX. I'll not offend anyone over here. But we might need to make custom software to be able to expose maybe out-of-order communication of some sort, or ability to chunk data across multiple paths, for example, and things of that sort, to be able to work around such issues. Okay, that's with respect to the network architecture itself. Let's take a quick look at the software stack or the model architecture stack as well. So the model architecture needs to scale to, first of all, 24,000 or 48,000 GPUs. 24,000, there are two different supercomputers, scale to 24,000 GPUs. And we can't simply use data parallelism. Our global batch size is it's fairly small, that we use about 2K batch size. So we can't scale it. Even if we give one sample per GPU, we can't go beyond 2000 for our data parallelism because it's limited by my batch size. And typically we want more than one sample per GPU. So we need to come up with multi-dimensional parallelism techniques, which include some form of data parallelism and model parallelism to be able to scale to this large supercomputers. So for Llama 3, we use 3 levels of parallelism. Llama, the next Llama will have more, but for Llama 3, we use 3: data parallelism, pipeline parallelism, and tensor parallelism. So this allows us to essentially build it as a Cartesian. So each dimension of the Cartesian can be based on how many samples I have, how much I want to split the model, and so on. Data parallelism obviously splits the global batch size. Pipeline parallelism splits the model, the layers of the model across the GPUs. And tensor parallelism splits the tensors across the GPUs. Now, what this means from a network perspective is that when I'm doing communication, I'm no longer doing a global communication that includes all the GPUs. I'm only doing communication across each dimension. So I'm doing a data parallel dimension communication, pipeline parallel communication, tensor parallel communication. And we have many such communications going on. So if we just take an example of data parallel communication, so how many GPUs do we have? We have 4, 16, 32 GPUs. And my data parallel dimension only has two processes, 2 GPUs. So when I'm doing communication across the data parallel dimension, each collective operation only has 2 GPUs, but I have 16 of these collective operations happening in parallel. And the trick is each collective operation at the communication libraries layer is not aware of the other 15 communication operations that are happening at the same time. So when each collective is dumping data over the network, it does not have a global picture of all other 15 collectives that are happening. And this makes it harder for it to communicate in a way so that it's not conflicting on the network routes with the other operations. That's really the challenge that we need to solve. Okay, that's with respect to the network. Let's take a one step higher and see where we are at with all these constraints. So first thing, power is a key basic resource. Okay, Meta is committed to sustainable data centers, 100% renewable energy. So the infrastructure has to be very power efficient. This is something Meta had made a decision a long time ago, and we stick with that. So it makes it very hard for us to get a lot of power. So we try to be as efficient as possible. This is a little different from other companies. For example, like Amazon just bought a nuclear powered data center, which is clean energy but not renewable energy. So we kind of differentiate that as well. So it is a very important resource for us. So we have to be very careful in how we spend that. And a lot of design decisions that we make for the data center, for the system overall, are influenced heavily by this big constraint that we have to work around. Some examples over here, optics versus copper. One of them is more expensive, but is more power efficient. So we tend to pick that in many cases, optics in many cases. We buy a lot of GPUs, but we run each of them at lower power. The reason is that even though I'm not getting the best performance out of each GPU, as an aggregate, as a full supercomputer, I get higher aggregate performance if I buy more GPUs and run them at lower power and assume that my network will do its job and will be able to scale well. Then buying more GPUs at lower power is more performant than buying lesser GPUs and running them at full power. So that's the another trade-off that we make. And of course, we are also building Meta internal silicon for more aggressive perf per watt optimizations going forward. A quick look at the reliability or unavailability events for the system. So we measured a 54-day snapshot period. So first of all, the training runs for many months. Llama 3 training ran for many months. We took a 54-day snapshot over there to study the interrupts that are happening. We had a total of 466 job interruptions. 419 of those were unplanned. And TLDR is that the GPU issues were the top category of failures, accounting for close to 60% of all of our unplanned failures. The top failure modes were faulty GPUs or GPU HBM3 memory and software bugs. In many cases, it was the GPU driver stack, but also included other parts of the software stack as well. And at fourth, this is just the top 4 listed over here. We also had some failures on the network switch and cable side, but relatively small compared to the number of interruptions we had from the GPUs. So this is something to keep in mind at the scale. We have continuous interruptions is a fact of life when we are running at that scale for that long. And another interesting thing I want to point out is that on soft errors, soft errors are deadly. These are, if you have a hard error, if a GPU dies, for example, the job will fail. So we'll know, immediately we'll know. Soft errors are tricky because if a GPU is working, it's working, but not quite optimally. And it's a synchronous training job. Just one GPU doing that would slow down the entire training because it's synchronizing at every step. So there were cases where our training performance, this example is actually a very extreme example. Our training throughput dropped by 50%. So this is an obvious example, right? You can look at it and say, oh, something went wrong. My training performance is 50% dropped. So we can go and debug it and figure out what happened. But imagine what happens if the training performance is 5% lesser or 2% lesser, right? How do we detect such errors, soft errors going forward? So we have very sophisticated diagnostics to do that, but they're never perfect because, very small drops in performance, we have to very carefully study to tune that correctly to be able to diagnose such things correctly. One fun fact I can mention is that while we were doing Llama 3 training, every day, midday around afternoon time, when the temperatures are very high, the training throughput drops by 1 to 2%. This is a natural occurrence because the temperature outside is very hot and we use air cooling. The GPU gets thermal throttled more often than when it's a cooler at night, for example. So that causes the training throughput to drop a little bit, 1 to 2% every day around midday, and by night it'll go back up to good performance. So this is a natural occurrence. It just happens every time. It's you can consider it as a soft error, but it's not really an error. It's just an artifact of how the environment is. There's nothing we can do about it. So lesson learned for us is run it in the winter, do your training job in the winter, so we can get a little bit more bang for the buck for our systems. Okay, how am I doing on time? Let's see, 10:42. All right, let's switch gears a little bit. Let's talk about serving the part of. So after we are done, we need to serve the model. What kind of things do we need in that? Okay, serving Llama 3. So this part you should all be aware of. There is, you can go to any system, you can go to meta.ai and type a query, any query that you like. And over here, I type what is the fabric. You get a response from that saying here is what it is about. In the back end, of course, there are two things that we should be aware of to get this response. The first thing is that it's called what is called time to first token. This is basically if you run the job, if you send a query, the first word, how much time after you send the query before you get the first word response, right? That's the time to first token. Typically, we need this to be in the order of seconds. The lower the better, obviously. And this part is very compute intensive and network bandwidth intensive because it sends a lot of data around, moves a lot of data around to get to that. That's the first part. The second part is what is called time per incremental token or time to incremental token. This is after you get the first word back, how long does it take for you to get the second word back, to the third word back, and so on. This is in the order of hundreds of milliseconds. This is very memory bandwidth intensive. It's not network bandwidth intensive because it doesn't move a lot of data, but it's very network latency sensitive. So how much time you take for the first byte to get transferred is very important in this case. All right, so again, as I said, there are two parts to it. The prefill part, which is more important for the time to first token, and the decode part, which is more important for the time to incremental token. So let me focus more on the decode part, the latency part of it. These are small messages, well, small-ish messages, less than a megabyte, sometimes tens of kilobytes. And these need to occur fast from a latency perspective. So we need to finish the collective as quickly as possible. And this is not easy to do. So for example, if you look at NVIDIA's Nickel communication library, there it goes through a bunch of steps to get through this. One is there's a compute buffer that is sitting on the GPU. It needs to gets copied into some temporary buffers. It goes to the RDMA NIC, transfers over the RDMA NIC, gets back to the other side, and finally goes to the compute buffer. And there's a CPU proxy sitting on top that orchestrates the usage of the RDMA NIC. GPU itself is not directly triggering the RDMA operation. So in this case, there are a few things to note. One is the GPU data, the first byte of GPU data going to the RDMA NIC, that itself is bottlenecked by other aspects of the GPU system. For example, the GPU memory has to be flushed. If I am running a CUDA stream, I need to I need to launch a coda stream to block other work that is going on. And of course, my control messages that go between the two CPUs also plays a role. All of this together, even for a very small collective, and just let's assume for even without an RDMA NIC, our latency is 20, 30 microseconds. If you add an RDMA NIC, that goes to 40 microseconds or so. Now, this is a very high latency number because, as all you network experts know, if I'm moving like a byte of data, it should be taking me less than a microsecond. I shouldn't have to spend 40, 50 microseconds to do this communication operation. And this is something, it's highly desirable, but also very hard to achieve, because fundamentally GPU and NICs are two separate decoupled entities. It's very hard for them to be able to access each other's internal state to be able to do low latency collectives, easily do low latency collectives. And this is a problem, of course, many vendors are looking to solve. For example, NVIDIA is looking at building out more tightly integrated network systems like NVLink Scale-Out, for example, which they recently announced. And other companies are following suit as well for looking at how we can bring these to a very low latency communication capabilities. All right, last piece I want to talk about is infrastructure fungibility. So we talked about all the infrastructure needs that are needed for our generative AI models. But I want to take a step back to see what we need to look at from a broader infrastructure support perspective. So I mentioned this earlier. Traditionally, our infrastructure was all based on recommendation, ranking and recommendation models. So they have a very different characteristic, if you will. They don't use a lot of flops. They don't do a lot of computation, but they rely on other things. Like, for example, they do a lot of network all-to-all sort of communication. They do irregular memory accesses and a bunch of other different things. So you can see on that table over here, ranking and recommendation models like take about 100 gigaflops per iteration. Serving or inference takes about a few gigaflops per second and about 100 millisecond latency. If you look at generative AI like Llama models, and this is even a much older model, right? This is Llama 65 billion tokens. The amount of flops needed for training is much larger. 1 petaflop per second. Amount of flops needed for serving is also much larger. So much more compute intensive than recommendation models, and they run at a much larger scale because the compute needs. So the number of GPUs they use is much larger as well. But the network access is more regular, if you will, or closer to scientific computing applications, if you will, where you're doing more Cartesian style communication. You're communicating across each dimension of your Cartesian grid. Recommendation models, on the other hand, are doing this weird all-to-all communication or all-to-all-V communication, if you will, where everyone is communicating with everyone. Makes it a pain in the neck from a network perspective to optimize that, because if I'm doing an all-to-all-V communication across all my processes, I can't scale it to 10,000 GPUs. It's very hard to do that, because imagine doing all-to-all-V across 10,000 GPUs. And I can't do rail-based communication networks, for example, in these. It becomes very hard to do all-to-all communication. So from a infrastructure build-out perspective, this is the decision we need to make with respect to how should we build out. We can't just custom build everything for generative AI, because then we can't support ranking models. Similarly, if we custom build everything for ranking models, we are spending a lot of money on generative AI. If the system with the architecture is not suited for generative AI or is less optimal for generative AI, we are wasting a lot of money. So this is a trade-off that we need to make. This is something we think about every day. There's no perfect solution, but it's something we want to strike a balance. So you will always notice some strange things in our design. saying that, hey, if you did it this way, it'll be more optimal for generative AI. We intentionally made that trade-off because generative AI is not the only product we need to support. We also need to still support our ranking models like ads, for example. And here's a kind of a picture that shows what different areas require. For example, if you look at the ranking and recommendation charts, they are on training, for example, they're more intensive with respect to network bandwidth, memory bandwidth, or irregular access memory bandwidth, if you will, and things of that sort, but not as intensive on compute. Whereas generative AI training is more intensive on compute and scale, number of nodes, but not as intensive on memory bandwidth. So this is a trade-off that we need to make. Building a supercomputer that is a superset of all of this is just incredibly wasteful. We can't do that. It'll cost a lot of money. So we need to, in some cases, specialize a few things, but in some cases, try to keep it as fungible as possible for our other workloads. Okay, almost at time. So just quick parting thoughts. So first thing is scale changes everything. In our experience with Llama 3, we never found raw performance to be the core, or very rarely found raw performance to the core problem. Performance is always based on, in this weird situation when something happened, what is the performance I would get? I'm almost always limited by that, not with respect to the raw performance the hardware can give. Could be based on power, physical layout, system reliability, physical constraints, and so on. Training and serving are both very important, but they require very different, from a network perspective, they look very different. Training focuses on scale, obviously. Serving focuses on latency of response. These unfortunately go hand in hand. You cannot build an amazing system, do a very large model training, but if you don't have a good enough system to serve it, it's pointless. You have a trained model, but you can't serve it. It's not serving the purpose maybe. And of course, hardware fungibility is very important, which forces us to some decisions which we would not have otherwise made, so that we can reuse the hardware for other models as well. Okay, that's it. I want to, sorry, I know this is not good etiquette to show in a keynote, but I want to just call it out. We are looking for people to work with us. We have, there's a QR code if you're interested in learning more. We have, of course, full-time opportunities, internships, sabbaticals, research collaboration, and whatnot. So if you're interested, if any of this sounds interesting to you, please reach out. We would love to work with you on this. That's it. Thank you very much.
Hey, Pavan, thank you so much for very interesting talk. So Slack exploded with questions. I would have to cherry pick probably. So I have the privilege to cherry pick the questions that overlap with my questions. How much time? I hope we have enough time for questions because there is a lot. So first, very long questions, I will break down to 3 smaller questions. What is the solution for instantaneous power draw on tens of megawatts after checkpointing?
If you have a solution, I would love to hear it. We work very closely with power companies because it is a big problem where when we restart a job, three problems, if you will. One is when you restart a job, your 24,000 GPUs are coming up. So they'll draw a lot of power when they come up. Second problem is things like checkpoint. When I'm checkpointing, I'm stalling the GPUs. I'm drawing, I have a dip, medium-sized dip on the power. And the third part is communication. Whenever I'm doing stalling and communication, my GPU is not active. So I see a smaller dip. So I have a large dip on restart. I have a medium-sized dip on checkpointing, and I have a small dip on collective communication. From what we can tell from the power companies, the large dip is not the problem. The large and medium dips are not the problem because they have worse customers than us, apparently, who draw even more power So that's not the problem. I think the bigger problem is more with respect to the spikiness when we're doing collective communication. That is an unsolved problem, unfortunately. And if you have any smart solutions, we are happy to hear those.
Another one, for the message sizes you're using for Llama training, how does InfiniBand compares to Rocky?
We did not notice any performance difference between the two, end-to-end performance for the models. In some cases, one does better, some cases the other does better. But at the end of the day, we didn't have any major differentiation between the two.
Okay. Any plans for question-specific A-trail, I would say multi-rail, optimized network instead of doing top of the rack?
Yeah. Yes. So we are looking at multi-rail systems as well. One of the things I wanted to that was my fungibility set of slides. Multi-rail is great for generative AI in the sense that we are doing more Cartesian style communication. So I don't need to have an all-to-all connectivity or a first hop all-to-all connectivity with all GPUs. So multi-rail seems more natural in those scenarios. But imagine we're using the same infrastructure for recommendation models, which are doing all-to-all communication. In those cases, multi-rail is going to be horrible because almost all communication is going to the top-level core switches. The rail itself is not very useful. There are some tricks we can play, like GPUs communicate over NVLink first and then send over a multi-rail, but then we lose zero-copy communication in those cases. So TLDR answer is we are considering, of course, multi-rail communication, but it's not as easy as, hey, it performs well in this case, we'll just turn it on. We will lose fungibility with our recommendation models heavily if we do that.
Great. Another question, not directly network related, but still very interesting is, can you provide next level of details of what kind of diagnostic you use for detection of hard and soft errors? Is there some ML-based heuristic or it's rule-based heuristic? I don't know if you can share.
Yeah, so I can share for the hard errors. For the soft errors, unfortunately, we don't have a good solution. I mean, we monitor, we throw some alerts when the training performance drops, but it's very ad hoc in some sense. So nothing to boast about in some sense. For hardware failures, like for hard faults, however, we have a very sophisticated set of tooling. We modified all through the stack. We modified Nickel, we modified PyTorch, we modified the models as well as all our tooling infrastructure to quickly detect and show throw errors and what we call localization, exactly detecting what went wrong quickly so that we can repair and move on, or even before repairing, can restart the job on a different set of nodes. The paper has a lot more details. I think we have an entire section on what kind of faults it detects, including we went and modified Nickel to have PyTorch have direct access to the internal state of Nickel. So it can tell when some part of communication dropped, it can dump that information saying that, look, here, this collective, this operation to this process stalled or failed or whatever it is. So we can diagnose it a lot more easily. It's hard for me to talk about it directly in this talk, but the paper has a full section with a lot of details on this part.
Great. I believe we still have time for questions. One question probably we'll try to squeeze in. Can you elaborate a bit more on the next level of parallelisms beyond 3D parallelisms that you guys thinking to explore?
I don't know if I'm allowed to share that part, but there is a lot of literature in the community with respect to other forms of parallelism that exist. I think NVIDIA published a paper on the Megatron, which talks about 5, I think, or 6 levels of parallelism. Apart from the 3 that I already mentioned, there is also expert parallelism, there is context parallelism, there is sequence parallelism. various other forms exist. But sorry, I can't. For next version of Llama, you'll have to wait for the Llama 4 paper.
We will wait. Do you have time for one more question? I'm asking the organizers because I don't have schedule in front of me. I think we kind of on borderline. I will go for one more bonus question. What is the increase in storage needs from just text only Llama training to audio and video Llama training?
Yeah. So from a tokens perspective, it's whatever number of tokens that we put. As we are increasing the number of, so there are two parts to it. Llama 3, the pre-training overall happened on text-based data, which was the big job that ran for many months for a lot of GPUs. Then we did post-training for adding images, videos, and so on. So the post-training jobs are not that large. So the storage needs in Llama 3 generation were not that large for the images and videos because it was a part of the post-training. It wasn't part of the main pre-training foundational model. That might change in the future, in which case our storage needs will dramatically increase based on these. But for Llama 3, it was not a big problem, mainly because it was a part of post-training, not a part of pre-training.
Okay, so thank you very much for taking time and answering questions. If you have extra time, you can jump on Slack. There is many more questions in the chat. And people, there's tons of so you're like a lot of work if you have time to answer all of this. Really appreciate time presenting. It was a super interesting talk. Really excited to hear about all the infrastructure. I personally would love to learn even more, so I will be posting more questions as well. Thank you so much.
Thank you, Pasha. Thank you for having me.